Good morning, class. Not sick, it's just allergies. So we're going to review the homework I gave you yesterday. And here are my glasses. 450 is the first one. And it says determine the oxidation number for the indicated element in each of the following compounds. Titanium in titanium dioxide. So typically oxygen has a -2. There's 2 of them here, so you get -4. Because the overall charge on this is 0, this has to be +4. B. Tin and SnCl3 with a -1. Chlorine, being a halogen, is usually -1. There's 3 of them, so total should be -3. Something brings it back to -1. It means the tin has to be +2. C in oxalate. You'd expect something, oxygen is -2 normally. There's 4 oxygens, so you would expect it to be -8, but it's only -2, so something brought it up by 6. That's got to be these 2 carbons. Divide that by 2, it tells you that each carbon is at +3 oxidation. And in hydrazine, when you put hydrogen with a nonmetal, it will usually be in a positive oxidation state. Clearly, nitrogen is more electronegative than hydrogen, so nitrogen is going to be the one with the negative oxidation state. So we're going to assume that hydrogen has its +1 state here. There's 4 of them. You would expect it to be 4+ because of the hydrogen. It's 0 overall, so that means that something is -4, and that's going to be the nitrogen, of which there are 2, so that means the nitrogen is at -2. nitrogen and nitric acid. Nitrous acid, sorry. So this normally dissociates into hydrogen and nitrite anions. Oxygen is -2 normally, of which there are 2, so you expect a -4. It's only -1, so the nitrogen has to be +3 in this case. Chromium in dichromate. So the oxygens should be -14. The dichromate is only -2, so something's pushing it up by +12. And because there's 2 chromiums, it means that each chromium is at a +6 oxidation state. So that's number 50 done. Let's look at 52 next. Did you guys try doing your homework? It'd be nice if you checked in too. So I'm amazed because I had a class of 30 students at one point, and now I have 4. I just have to pick up the phone. There's people hoping that they're going to get a chemistry diploma without actually doing anything.
Not if I can help it. Okay, 52A. So the first one, it says, which of the following are redox reactions? For those that are, indicate which element is oxidized and which is reduced. For those that are not, indicate whether they are precipitation or acid-base reactions. Okay, so
Copper hydroxide, which is a solid, reacting with 2 nitric acid, aqueous, to yield copper nitrate. Aqueous plus water. This is an acid-base reaction. There's no reduction or oxidation. The copper stays at +2. So you've got 2 hydroxides, which are -1, and 2 nitrates, which are both -1. So this means the copper stays at +2. The copper doesn't change oxidation state, and what happens is the hydroxide meets with the hydrogen. So the net reaction here is hydroxide, 2 hydroxides are neutralizing 2 hydrogens to give you water. So it's an acid-base reaction. B shows iron oxide combining with carbon monoxide to give you elemental iron and carbon dioxide. That is actually a redox reaction. Okay, so what's going on here is the iron is turning into elemental iron. So the iron here is at +3 oxidation state because it's combined with 3 oxygens, which are a -2. So 3 times -2 is -6. That's something's got to be +6. There's 2 of them, so the iron is ferric. So ferric iron is now being converted to elemental iron with an oxidation state of 0. 2 of these go to 2 of these, so that means 6 electrons are in the mix. They're being added to this, so this is being reduced. This is a reduction reaction. And what's happening to carbon monoxide is it's being oxidized to carbon dioxide. So in this, what's happening? This is -2, so this has to be +2. This is also -2, but there's 2 of them, so that gives you -4, which means the carbon is now +4. So the oxidation state of carbon has increased. Carbon has lost 2 electrons. So that's an oxidation. So this is actually bringing to light the process they use for smelting iron. When they smelt iron, they get iron ore out of the ground, which is in the form of iron oxide. They heat it up to a high temperature and they expose it to carbon monoxide. The carbon monoxide basically scavenges the iron away from scavenges the oxygen away from iron. Because everything is super hot, the iron goes to the bottom of the container. So you have basically you get a pool of liquid iron forming at the bottom of the container. Once it gets thick enough, they open a tap and they let the iron pour out and they form ingots out of it. And that's how they smelt iron.
C.
Shows you strontium nitrate, reacting with sulfuric acid, and it yields strontium sulfate. Solid, and nitric acid.
It's asking you
Whether precipitation, this is a precipitation reaction because you have 2 aqueous solutions and it's producing a solid. This is a precipitation reaction. Let's put it over here. Precipitation reaction. Now, are there any spectators? Yeah, the nitric acid is a spectator here because these stay dissociated. So what's really happening is you have strontium cations. This is the net ionic equation here. Morning. The net ionic equation goes like this. So the final product is strontium sulfate is a solid. So that's a precipitation reaction.
It's fine, honey.
D. The board is so wavy, it's hard to erase. In this fourth reaction, we have zinc plus 10 hydrogens plus the nitrate anion, aqueous, giving you 4 zinc cations and dinitrogen oxide and water. So we have to determine what's being oxidized and what's being reduced. The zinc is turning into zinc ions, so zinc, which is at 0 oxidation state, is turning into zinc at +2, so that means it's been separated from its electrons. It's been oxidized. And the nitrogen in nitrate is being reduced to dinitrogen oxide, and the hydrogen stays a +1. These hydrogens don't enter into it. So you have nitrate being turned into dinitrogen oxide. So if you look at the oxidation state of the nitrogen here, you got -2 times 3 should give you -6. It's only at -1. It means the nitrogen's +5 in the nitrate. In the dinitrogen oxide, oxygen is still -2, but the overall molecule is 0. So that means that each one of these nitrogens is at +1. So the nitrogen has gone from an oxidation state of +5 to an oxidation state of +1. That means it's had 4 electrons added to it, which would mean you'd have to run this equation times 2 to get the sufficient electrons. All right, so you do have an oxidation and you have a reduction. There's the reduction, there's the oxidation, the 2 are coupled, so that's a redox reaction. And Mama's standing right behind the camera, watching me talk. What a peculiar cat. Handsome too. Look. Look how handsome he is. Hey Mama, say hi. And he's not too talkative. D. Next one is 62. Calculate the molarity of a solution made by dissolving 0.145 molar sodium sulfate in enough water to form exactly 750 milliliters of solution. Okay. So you're going to use molarity is equal to the number of moles of the solute divided by the volume of the solution. And they're asking you to calculate the molarity, so I've got the equation already. So 0.145 moles of sodium sulfate. And you want to make exactly 750 milliliters. So 750 milliliters is 751 thousandths of a liter. Remember, the definition of molarity is moles of solute divided by liters of solution. So the molarity of the solution would be 0.145 divided 0.75. I got my calculator to work again by dropping it. Probably the battery was getting loose or something. So it works out to 0.193 recurring moles per liter. How many sig figs are we allowed? I guess 3. There's a decimal place after the 750, and the answer is no. But let's say 3 sig figs anyway. So it's 0.193. You can leave it like that, or you could say 1.93 times 10 to the minus 1 molar. 462b. Says how many moles of potassium permanganate are present in 125 milliliters of a 0.085 molar solution. So again, start with molarity, E is equal to number of moles divided by the volume. Therefore, you can rearrange it to say that the number of moles is equal to molarity times volume. The molarity, we're told, is 0.085 moles per liter. And we are also told that the volume is 125. So 125 thousandths of a liter. Liters will cancel. And what you get is 0.085 times 0.125, or 0.0106625 moles of what?
62 potassium permanganate. So they're asking for moles. We're finished.
Just write it with the correct number of sig figs. That's going to be 0.0850. Yeah, they put a 0 after it. So that's 3 sig figs. So you're going to say 0.106 moles KMnO4, potassium permanganate.
Let's do C now. There is a C. Yeah.
Okay, and the question asks, how many milliliters of 11.6 molar hydrochloric acid solution are needed to obtain 0.255 moles of NaCl? You're looking for this quantity, so you're going to rearrange it. N is equal to mv. Now let's plug in the numbers. The molarity is 11.6, and the volume is, oops, no. Milliliters, no, that's not what we're looking for. We're looking for this. So we're going to rearrange it to have V by itself. So V is equal to N over M. Sorry about that. The number of moles is 0.255. The molarity of the solution is 11.6. So 0.255 divided 11.6 will give us our answer in liters, and then we'll multiply by 1,000 to turn it back into milliliters. So 0.255 divided 11.6, it gives you 0.021982758 times 1,000 milliliters per liter, and we get 21.9827. We're really only allowed 3 sig figs, so we're going to say 22 milliliters.
Hope I didn't do this yesterday already. No, I don't think so. And the other one for homework was 478. It says what mass
says, what mass of NaOH is needed to precipitate the cadmium ions from 25 milliliters of 0.5 molar cadmium nitrate? So we're starting off with cadmium nitrate. And you're precipitating with sodium hydroxide. You're told that there's 25 milliliters of this, and its concentration is 0.500 molar. And what they're asking for is how many grams of NaOH. They say what mass. That's essentially grams. So you see what I did here? I wrote out everything that the question is telling me. Lay it out. That way you can see what they're asking, and it's easier to set up the problem. Cadmium is a divalent cation. It means it's got a +2 charge. Let's write down what the reaction is. Again, you get cadmium hydroxide as the precipitate. The other thing is sodium nitrate, which is aqueous. It's a soluble salt. You get 2 of those. You might say, how do you know that, Mr. Botsy? Well, they're saying in the question, precipitate the cadmium ions. So you're assuming that this reaction causes precipitation of cadmium ions. How do you know it's going to precipitate? Well, by combining with the other ion. So the only other thing it can combine with is the hydroxide. If you leave it in nitrate form, nothing happens. So that's how I know this is what you get. All you do is you switch your metals. Those are the products, okay? That's not soluble. They're telling us it's not soluble. That's how I know to write the rest of the equation. And there's one other thing you have to pay attention here. For every 1 mole of cadmium nitrate, you're going to need 2 moles of sodium hydroxide. So you've got to take that into account when you do the calculation. So first we're going to find out how many moles of cadmium nitrate we have. We know that molarity is equal to the number of moles divided by the volume. So if we arrange the equation, we can get N is equal to mV, and just simply plug in the numbers. We have 0.500 mole per liter multiplied by the volume, which is 25 1,000ths of a liter. Liters cancel, and we get that the number of moles of cadmium nitrate is 0.5 times 0.025, or 0.0125 moles. Cadmium used to be a useful substance for making the first generation rechargeable batteries were nickel cadmium batteries. And cadmium is a very toxic metal. You do not want cadmium in your body. So if you improperly dispose of cadmium containing batteries, you're actually contributing to poisoning the environment. There was an incident that happened, I think it was in Japan, where some cadmium was leaked into a river because of sloppy mining operations, and the river was next to a rice paddy. They used the water to irrigate the rice. The rice became contaminated with cadmium, and then a whole bunch of people got cadmium poisoning. Cadmium poisoning, what it does is it destroys your bones. It destroys the bones that are supporting the most weight. So basically it causes your vertebrae in your lower back to break. And it causes a disease called itai, which means it hurts, if you can imagine why they called it that. So, yeah, don't throw away cadmium batteries. Dispose of them in the dump appropriately. So 0.0125 moles of cadmium nitrate are present. We're going to need twice as many moles of the sodium hydroxide. So we're going to say times 2 moles of sodium hydroxide for every 1 mole of cadmium nitrate. Oh, I should have written this was moles of cadmium nitrate as well. Forgot to write it in there, sorry about that. Okay, the moles of cadmium nitrate will cancel, and you get 0.0250 moles of sodium hydroxide. So now we're going to multiply by the molar mass of sodium hydroxide. So we're going to say 0.0250 moles NaOH times the mass of sodium 98977, mass of oxygen 15.394, and the mass of oxygen 1.00794 grams per mole. Let's see what that equals. So open the bracket, okay, times 2 equals, times open bracket, 22.98977 plus 15.394 plus 1.00794, close the bracket, multiply, and you get 0.9992775 grams of NaOH. And where I come from, that's pretty close to 1. So you need 1 gram of sodium hydroxide to precipitate the cadmium. And that's that for the homework. Now, I'd like to give you just a little bit of notes. So bear with me. I showed you yesterday, I had up to titration. And I showed you the notes. This is what I did yesterday. I didn't do all that much. But I want to go over the notes together as well. There's a couple things in there that I'd like you to take note of. I'll just show you what my notes look like. You can copy them later. So I left off here when I showed you my notes last time. I've added some more. I haven't had a lot of time. There's the bottom half of the page. And I did a little bit on the next page. It's a practice example. Yeah. Okay, so that's the practice examples worked out. What I want to draw your attention to in the notes is, they're no good to you if I don't show you the actual pages that they were coming from. Page 152 in the notes. So the 152, there's the practice examples, the ones I just showed you. See if I can get them close enough to you so that you can actually read the page. So the practice example is that one for page 152. Then there's a practice example on page 154 that I'd like you to have a look at. Which is that one. $154. Yeah. I think I just pause the okay, and I'll show you the next one so we can also work it together. Practice exercise on page 155. So you can always go back to the video and pause it and try the problem. When I give you the homework, I'll show you the problems that I'd like you to try tonight. But here's what I wanted to draw your attention to, what all this stuff boils down to. It's really quite easy. And that is, whenever you do stoichiometry and chemical analysis, and solutions analysis, titrations, all the calculations in chapter 3 and 4 boil down to this little algorithm. You go from grams to moles, moles to moles of something else, and then moles of something else to grams of something else. And all the transitions, the first transition you divide by molar mass. Here you use the stoichiometry. Here you multiply by molar mass to get back to grams. And then if you have a conversion of number of grams to moles or volume, you use that the molarity is equal to the number of moles of solute divided by the volume of the solution. So this is molarity. This is number of moles. The molarity is in units of moles per liter. And this is the volume of the solution in liters. And the last equation that you use is M1V1 equals M2V2 for titrations and for precipitations. Okay? And for dilutions. All three of those, you can use this formula. So for titrations, you'll have an acid with a base or maybe a redox titration. If it's a redox titration, don't forget to keep track of the stoichiometry as well. If you have a precipitation reaction, it works just like an acid base. And if it's a dilution, remember that because M1V1 is equal to N, which there was a small interruption there. Remember that with dilutions, because the molarity times the volume is equal to the number of moles, you can also have a titration or a dilution where you recognize the fact that, for example, in a dilution, you recognize the fact that the solute amount does not change. That's why it equals this number N. Here you're just adding solvent, right? So same amount of solute, but the volume of the solution changes. So of course the concentration of the solution changes as well. But the amount of solute stays constant unless you take some or add some to it. I'm going to stop it there for today, but here's what I'd like you to try for homework. Okay, try a couple problems for homework in the titration section, and I'll show you the titration. Try 77, 78, and 70. Have I not already given you one of them? Yeah, I already gave you 78. So try 77 and 79. We haven't done that yet. So try 77 and 79 for homework tonight. Where is it? 77, 79, they're here. Okay, so do 77 and 79. Just pause the TV. It's not focusing. Pause it and copy the question, and then you can try it, and I'll give you the solution tomorrow. Okay? I'll see you guys tomorrow.